And let me share my screen. Are you able to see my screen? I hope you are able to see my screen. You know, I have got your chat window also open, so you can ask questions. Are you able to see the screen, please?
Yes, sir.
Yes, sir.
Okay, good. So I hope you all attempted the quiz last time. How was it?
It's good.
It was okay, right? See, in the general section, I have posted some background question to get some feedback from you people. Please fill that poll in the general section of Teams. This is the first time I'm trying the poll, so maybe you didn't get an intimation that this poll was to be filled. If you go to general section, you'll find two simple questions. You know, they are about background. They are not about anything you learned in this course. So please fill them up. Okay, so last time what did we do? We did some closure properties of finite automata, like regular languages are closed under union, intersection, complement, catenation, Kleene closure, reverse. And then we did some decision problems on finite automata. That is, given a large finite automaton and a word, can we determine whether a word is accepted by the automaton? That is called the membership question. Another question we did was, given a large non-deterministic finite automaton, can we determine whether any of is its language empty or non-empty? That is, how do we determine whether the language of an automaton is empty or non-empty? The language is non-empty if and only if there is a path from one of the start states to one of the end states. And you know, we can collect the labels on this path, ignore all epsilons, and we'll get a word which is in the language. So if there exists such a path, there will be a word which is in the language. So this is the way to determine, you know, whether language of an automaton is non-empty. And finally, we saw what is called language inclusion or language containment problem. Language of, given two NFAs, N1 and N2, we want to check whether the language of N1 is contained within the language of N2. That is, every word accepted by N1 is also accepted by N2. But the reverse may not be true, right? And we saw that this could be done using the previous operations that we have done. So I hope you are clear about that. If there is any question about that part of the talk, let me know. Otherwise, we'll go ahead with today's topic. Okay, I don't think there was too much. So today's topic is what is called regular expressions. Okay, and it's an important topic. So we will learn this today. What are we trying to do? You know, we are trying to specify patterns of occurrences of letters. Now, this kind of thing occurs in many cases. You know, we want to specify, you know, what is a syntactically correct program, or we want to specify, you know, what is a noun, what is a sentence in English language. We saw some patterns that occur in defining sentences. So we want to specify patterns of occurrences of letters, right? And in order to do that, we define something called pattern expressions. Pattern expressions, right? So we define patterns of occurrences of symbols from some given alphabet sigma using something called pattern expression over sigma. And we already saw examples of this. You know, we, without actually formally defining it, we were using notation like this, you know, A star B. What does A star B denote? It denotes all words which have 0 or more occurrences of A followed by exactly one B. That is words like, you know, just B by itself, or another word which will be AB or AAB, or any number of A to the power n B, right? So A star B was a pattern expression which defined this collection of words. It defined a language, right? We have been seeing this informally, but today we are going to define this formally. Okay. So is the intention of a pattern expression clear? Okay. Next. Okay. We will use Greek symbols alpha, beta, gamma to denote pattern expressions. Okay. So, XYZ ranged over words and ABC ranged over letters and or symbols of sigma, and alpha, beta, gamma will range over patterns, right? Now, a word, given a word in sigma star, we want to check whether it matches with a given pattern or not. This is what we want to define. That is, we are given a word X in sigma star and we are given a pattern alpha, and what we want to define is whether X matches alpha or not. If it does match, which we will define, this is denoted as X belongs to the language of alpha. This is the notation we will do. So this is intended to show that X matches with alpha or X belongs to the language of alpha. Thus, language of alpha, L of alpha, is the collection of words which match with alpha. Okay. So is the notion of language of a pattern clear to you what we are trying to do? For example, what is the language of A star B? It is all words, collection of words of the form A to the power n followed by B. A to the power n is n occurrences of A, right? Where n is greater than equal to 0. And as we said, this will contain B, it will contain AB, it will contain AAB, etc. Right? This is the set that you will get, right? So language of a pattern like this is clear to you, all the words which match it, right? So I hope this is fairly straightforward. It is clear. Here we have a more complicated language, L A star. Here I have a pattern which says A star B plus B A star. And what does this denote? This denotes, first of all, this expression here denotes all the words where there are 0 or more A's followed by a single B. Okay, that is what we saw before. What does this this blue underlined expression, sub-expression denote? It denotes a B followed by an arbitrary number of A's. That is B followed by 0 or more A's. And this plus denotes union. Okay, so we will see this syntax more formally in coming slides, but intuitively such an expression says either a word which matches the left hand side expression or the right hand side expression. Plus is the union of the language of A star B and the language of B A star. So you can see what kind of expressions we are constructing. So we are using basic patterns like letter A, letter B. Then we are using operators like clean closure, union, etc. Union is denoted by plus, and then we get a language corresponding to this. So what will be the language of this expression? The whole expression, it will be either arbitrary number of A's, 0 or more A's followed by a B, or a B followed by arbitrary number of A's. So it will be A to the power n followed by B, or B followed by A to the power n, where n is greater than equal to 0, right? So intuitively, the language of this expression is clear to you, where plus denotes union. Any confusion so far? Okay. If there are any questions, please ask in the chat. Huh? Yeah. Okay. So I think what have we said? That basically we are trying to define patterns of occurrences of letters like this, these two examples that we gave. And, a word may match that pattern or may not match that pattern. All the words which match the pattern denote its language. And so here are the example of one pattern and one pattern expression and its language. Here is another pattern expression and its language. Okay. So now we are going to make this, everything that we said in this slide intuitively, little bit formal, right? So our patterns are going to be made from some atomic patterns and using some operator, like A, B, etc. And we will use some operators like star, clean, that is the clean closure, or plus, which denotes union, to make bigger patterns or compound patterns out of simple patterns, right? This is how it is. It's like arithmetic expression. We can have 1 plus 2 multiplied by 3, right? So we are using basic natural numbers as atomic expressions, and then we are combining them using operators like plus and multiply, right? In arithmetic, that is what we do, and something similar is being done here. Okay, so I'm going to define the notion of what are pattern expressions and what is the language denoted by this. So I have firstly I have this pattern expression called 5. So I'm going to define atomic pattern expressions. These are basic patterns, right, over a given alphabet sigma. 5 denotes a pattern where no word matches this 5, and I've written it in 5 to distinguish it from empty set. You know this empty set. This is empty set. Sorry. Empty set, right? And phi is the pattern that we have defined. You know, the pattern expression that we have defined. And the language of this red phi is the empty set. That is, there is no word which will be in the language of phi, right? So phi is the kind of thing that you write down on a piece of paper, and language is something that you calculate mathematically from it, right? And the language of phi is empty. There are no words which match with phi. I hope this is clear. Let A be a letter in sigma. Sigma is our given alphabet. Then red A matches a single letter A. It does not match anything else, right? So for example, you know, a word AB will not match with this, will not belong to the language of this pattern expression A. I give pattern expression in red. Okay. Now there is a subtle difference between this A in blue here and the A in red. This A in red is the symbol denoting the letter blue A. There is a difference between the red A and blue A, which is not, you know, later you'll be comfortable not having these colors, but this is like this. Suppose I want to write down number 101 in English, you know, in mathematics, I'll write down that this as 101. But this red 101 is actually a string consisting of a digit called 1, followed by a digit called 0, followed by a digit called 1. And this denotes a number, which also we call 101, but this lives in the world of mathematics. So this is a number, and this 101 is called a numeral, right? It's like a pattern that it's like a something that you write down on a piece of paper to denote this number, right? So we always denote mathematical entities by means of some symbols which we write down on paper, right? And these are numerals and these are numbers. Okay. Similarly, when we say 2 plus 3, expression 2 plus 3, what do we mean? We mean by number obtained by taking the number corresponding to numeral 2, which will give you blue 2. Then we will take the number corresponding to this numeral 3, and then we will apply a mathematical operation called plus, you know, over these two numbers, and this will give us answer 5. Okay. So you know, this red plus is the sign denoting the mathematical operation plus. Okay. All this is, you know, just to make things very, very clear. Then we understand implicitly what all this means, and we stop distinguishing between numerals and numbers, because, you know, in some sense they are representing the same things. This is just the representation of what is red is just the representation of what is going on in blue, right? So I hope this idea of numerals and numbers is clear to you. Okay. And we can see that, you know, a blue letter A will match with the red letter, red symbol, red pattern A. So this is the case. Whereas AB does not match with A. Okay. So I think we have 5 denoting empty set of words, A denoting only. What is the language of A? First of all, it is a set which has a single word in it, and that word is just the letter A. Letter A is also a word. You know, it contains only one sequence of one element, right? So
Sir,
this
I
is
have a
the,
question.
yes, please.
In that first, I mean, are these definitions or is this following from something?
No, these are definitions. So we are defining what are the kind of patterns, atomic patterns we have, which I list in red, and on the right hand side in blue, I am defining the language. So these are definitions. So I am defining here what is called syntax, on the left hand side in red, and its semantics, which is its meaning as a language together, right? So that's a good question. So here,
Okay, sir.
this
Yeah.
is semantics. And this is the syntax, and I'm defining definitions. So I'm giving a definition here. Okay, this does not follow from anything. Okay, is that fine?
Yes, sir, it's clear.
All right, next we have another symbol called red epsilon. Now remember, red epsilon is something you write down on a piece of paper, just as you write down the sequence of letters 101 to denote number 101, right? Red epsilon is a symbol, and its language consists of a single word, which is the empty word. Remember, this is different from the empty set phi. Sorry, I should write blue empty set phi. So this set is different from empty set, you know, not equal to phi, right? Okay, that's clear to you. But red epsilon is a basic atomic pattern, and its language consists of a set of single element, which is, and that element is the empty string. So this may be a little bit, you will get this clear once you see uses of these things, but just remember this definition. So we have three kinds of things which are atomic patterns: symbol phi, symbol A for every letter A in sigma, and an epsilon, red epsilon. Then we have got a hash symbol, and hash symbol matches any single letter from sigma. So language of hash is just sigma. So what will match hash? For example, A will match hash, but AA will not match. I'm not writing that belongs to, will not match hash, right? Because it is not a single letter, it is more than one letter. So any letter, A will match sigma, also B will match hash, etc., right? So hash denotes any single letter. Okay, that's the notation we will use. So language of hash is just the set sigma. Remember, sigma contains all strings, made out of alphabet sigma, where the length of the string is exactly one letter. Okay, and then we have got at. At matches any possible word from sigma. So the language of at is sigma star. So any string like ABA will belong to the language of at, right? Because any arbitrary string will be in the language. Every possible element of sigma star is in the language of at, right? So these are the 5 atomic patterns that we have got. The idea of atomic patterns is clear and the language is clear. There's not too much to say about it. It's just you got to, we will see this slide again and again. Right. Now, these are not very interesting. What is the point of defining just such languages? But these are basic languages. And now what we can do is we saw a lot of operations over languages, right? Like union, intersection, catenation, Kleene closure, complementation. What we will do is, using these basic languages defined by atomic patterns, we will now construct larger patterns, out of it, which will give more complicated languages. Just as given simple, in arithmetic, we have got simple expressions like 1, 2, 17, etc. And using these, we can construct complicated numbers, 2 plus 3 multiplied by 4, right? So here we are using these basic expressions and combining it with operators to get a complex expression denoting a more complicated number, right? Similarly, we will define compound patterns, right? And we use operations like catenation, intersection, etc. on languages to get more complex patterns. So I will give you a list of operators which you can use to combine basic expressions to get more complicated expressions. So given expressions, remember alpha, beta, gamma range over expressions. Given two expressions alpha and beta, I can construct a new expression alpha plus beta. Bracket is just used to denote the scope. You know, bracket is an extra symbol we use to make the scope of plus clear. So alpha plus beta is a more complex pattern. And actually plus denotes union. So what is the language of alpha plus beta? Firstly, you have whatever is the language of alpha you get, whatever is the language of beta you get, and take their union. So language of alpha plus beta is language of alpha plus language of beta. And that is how you can denote more complex operations. And we already saw an example of this here. We had this A star B plus BA star. Now let's say that we know how to calculate language of A star B, which is arbitrary number of A's followed by B. And BA star is arbitrary number of B followed by arbitrary number of A's. Then plus is the union of these two, right? And that is what, but that was that one particular example. Here we are defining it in general. So is the notion of alpha plus beta clear to you? And its meaning? Okay, we'll have alpha dot beta, right, which will denote catenation. We already saw catenation operation over languages. What is language of alpha dot beta? You first calculate the language of alpha, you calculate the language of beta, and then you catenate them. What is catenation? Take a word from alpha, take a word from beta, and catenate them. And take all such possible combinations and you will get this language, right? So we had already seen this language. Suppose I have got, you know, A star as an expression. What will this denote? This will denote words epsilon, A, etc. Right? It will denote a language like this, A, and so on. Arbitrary number of A's. Similarly, B star will denote what? B star will denote B to the power n, where n is greater than equal to 0. Same thing. I have written this in this kind of dot notation above. Here I have written it mathematically, right? So these two languages are given to you. Now what is the pattern A star dot B star, A star catenated with B star? What will this give? What kind of language will this give? Arbitrary number of A's followed by arbitrary number of B's, right? Because you can take a word consisting of arbitrary number of A's from the first language, catenate it with a word from the second language, which is arbitrary number of B's. And the number of A's and number of B's are not related in any way. So n and m both are independent, but they are greater than equal to 0. This is the language it will denote, right? So you know what is catenation. Any confusion so far? Okay, there are no questions, and this is a simple idea. Okay, one notational convention, alpha dot beta, we will write as alpha beta. We will omit the dot there, but implicitly it is there. It's like in numbers, we have x multiplied by y. We will often write as xy in mathematics, no? So similar convention is being used here, huh? Okay, so we will often abbreviate this by this. So catenation is clear to you, right? And finally, I will also be able to take Kleene closure of the expression. So the red alpha star will denote the Kleene closure operation, right? And what is the language of alpha star? We will first take the language of alpha, okay, and take the Kleene closure of it, which is what will we do? We'll take the language of alpha, take its nth power for all possible n's, and take the union of all these components. L alpha to the power 0, L alpha to the power 1, L alpha to that infinite union is what we will take. Right? So is the language of alpha star clear to you? By the way, there is a subtle point here which we already saw. This symbol red plus denotes union on the languages. This symbol red dot denotes the catenation in the languages, and this symbol red star denotes Kleene closure on the languages. Right? So the symbol and its meaning, the red and the blue should be clear to you. One is in the world of, operations on languages, and star is the notation for it. Okay. And then once we know what this means, we will drop the colors, because we will be clear about, when we are talking about expressions, we are talking about symbols. When we are talking about language denoted by the expression, we are talking about the corresponding operation on the language. Right? So Kleene closure. And in this Kleene closure, for example, we had a basic pattern A. What was its language? Can anybody tell me what was its language? What set of words will be in it? Its language? What is the language of a pattern A, atomic pattern A? We saw it here. Language of A is a set containing a string which is a single letter A, right? Because language is always collection of words, and so this collection of words has only a single element, and that element consists of a string which is a single letter A. Right? Okay. Now when I take A star, what is its meaning? It is the Kleene closure of this language. That is, I have this A and I take the Kleene closure operation over languages defined before. That is the blue star, which is equal to what? This A to the power 0 union A to the power 1 union this set to the power 2, etc. I take this infinite union, and what do I get here? This is equal to what? This set to the power 0 will give me what? I think I asked you to revise this yesterday, and not many people have done. What will this underlined red expression reduce to? Oh, sorry.
Epsilon.
Yes. So a set containing only string epsilon, right? Yes. So this will give us epsilon union. What will the second one give us?
A.
Sorry, I should write it. See that this color change is a bit of a yes, blue. This will contain string A. What about this third term?
AA.
Right. So union AA, and it will go on like this. So what I will get is basically A to the power n for n greater than equal to 0, arbitrary number of repetitions of A, right? Which is what we saw before. A star gave you 0 or more A's, and that is what it is giving you. But this is by this definition, by the Kleene closure definition. So what we were doing informally, now we have formally defined by this rule, right? So how I calculated A star is clear to you?
Yes, sir.
Okay, this is how you calculate the language of an expression. In fact, I will give you a better example. Consider this compound pattern, which we saw before. What will be its language? So let us ask that question here. There is this pattern given to you. Alpha be this pattern. What is this language of alpha? Can somebody guess and tell me? I have put brackets to make clear the scope of various operators. Okay. So what will it contain? It will contain language A star catenated with B. That is one one set of words in this language, together with plus is union, language words which belong to this sub pattern, which is B followed by A star. So what will I get? What will the first one give me?
A star B.
Yeah, which is arbitrary number of A's followed
A
by
raised
B. And the second one will give me
B A raised to N.
B A to the power n, where n is arbitrary, right? So this is the language we will get, correct? So you can guess this, and intuitively what you have done is what we will formalize next. You know what will happen is the following. So how do we evaluate a compound pattern like this? You know, this pattern is constructed out of atomic patterns using operators. And what are the operators we saw? We saw three operators, plus, dot, and star, right? We'll see some more operators also. But currently this pattern is made out of atomic patterns using the operators or constructs or compounding operators. So what is the structure of this pattern? It is made clear by the brackets, and I can actually draw what is called the parse tree. Let me write it in red. Parse tree. This is an important idea. So this pattern is basically saying you are at the top you are doing a plus operator, right? And this plus operator is applied to two sub patterns. What are these sub patterns? The left hand side sub pattern underlined in blue, and then the right hand side sub pattern. Now the left hand side sub pattern has the top operator dot, right? So I have a dot operator here, and that dot operator is applied again to two sub patterns. First is, something which is given here, which is basically obtained by applying star to the atomic pattern A, and this is applied to B. Whereas the right hand side consists of again a dot, which is applied to a B, and then it is applied to a star and an A. So this is called the parse tree, and it basically says in order to evaluate this operation, first you have to evaluate the left hand side operation, evaluate the language of the right hand side operation, and then apply the plus operator to it, right? In order to evaluate the left hand side operation, sub expression, you have to see its structure. Its structure is dot of something on the left and something on the right. So it's a dot of something on the left and something on the right. The thing on the right is just the atomic pattern B. On the left is a pattern of the form A star. So it's star operator applied to sub pattern A. So is the notion of parse tree clear to you?
Yes, sir.
Let me give an analogy. If you had 2 plus 3 multiplied by 4 in arithmetic, what does this mean? We have a star operator. This is in arithmetic. Don't confuse this with star here. So it has got two sub patterns. There is a plus. You do 2, you do 3, and then you apply 4, right? This is the way in which you calculate this expression, right? And this is called the parse tree, which is telling what are the basic numbers and what are the operations applied to it. This sub expression will give you a number. This sub expression will give you a number. Combining these two using multiply, you will get the value. So you can calculate the value of this expression, in a bottom up fashion. First, that this red numeral 2 denotes the number 2. This red numeral 3 denotes the number 3. There is this plus symbol which denotes the sum of these two, right? So you will do 2 plus 3 and you will get 5 here as the answer, right? So first you will get 2 here, you will get 3 here, you will get 5 here, here you will get 4, then you have to multiply 5 and 4 and you will get 20 here. So you are doing a kind of bottom up calculation of the value of this expression in arithmetic. Agreed? This is how you would evaluate an arithmetic expression. Right? And what we are going to do is we are going to do something similar to calculate the language. In fact, this method of calculating is very common for any kind of algebraic operation, So what do? We first calculate the language corresponding to the leaf elements, right? So I will do that, and I will write down that language B. First, I will get language containing only A. What is the language containing this? Only A. Similarly, for this A also, I will get a language containing A. Then I have got a language containing B, and then a language containing B. And these two are joined there is a star operator here, right? So there is a star operator here, which will give me what language? What language will I get here for this sub expression? For this
A
sub
star.
expression, A star, right? So I will, yes, I have to denote that set A star. So we know what this is. This is, I will write here A star, as you said. A star. This denotes the language A star. Similarly, here also there is a star operator and I get A star, right? And then I'm combining this by the catenation operator, right? So I will get A star B. And here I will get, I'm combining this using dots, so I will get B A star, right? This is a language, huh? Remember. And then I'm combining this using union, so I will get union set A star B, comma B A star, right? This is the language I'll get. So I'm calculating the language corresponding to this by first starting at the bottom, calculating its language, then applying star to it to get the language at the next level. Similarly, I start at the bottom, I calculate its language, then there's a dot operator. So this language and this language I catenate and I get this language. And similarly, I go up. And at each stage, you know, in this tree, there is a node which is labeled by an operator. At the bottom, I have the node which is labeled by an atomic expression operator, right? A. And I know how to calculate language for it. So I have the rule for atomic patterns and their languages. So for every atomic pattern at the bottom of the parse tree, I can calculate its language using these rules, right? Agreed? So bottom of the tree can always be calculated using these rules, because at the bottom of the tree, there can only be one of these 5 things. These are atomic patterns. Now, at each level, two patterns are combined using one of the operators like plus or dot, right? Or star. So what we can do is, we can take the language corresponding to the left subtree, language corresponding to the right subtree, which we know how to calculate. And then this dot denotes catenation. So I'll take catenation of those two languages, and that I define here. I'm saying here, for example, if the pattern is alpha dot beta, then I have to take the language of alpha, language of beta, and take the catenation. So if I already know the language corresponding to these two subtrees, you know, this subtree and this subtree, then I can calculate the language corresponding to this dot, because it denotes catenation. And every node will denote one operator for which I have defined how the languages of the components are to be composed, right? So I hope you will be convinced that by systematically applying these rules bottom up, we can calculate the language for the full expression. Any confusion here? I know this is all very obvious. You do this when you calculate arithmetic expressions, but this pattern of working, you know, is called inductive definition of the language. And this pattern is very, very common in computer science, even in mathematics, and many things are defined using it. So I can summarize this. Every pattern expression is uniquely constructed from, what is the pattern expression made out of? Atomic patterns by successive applications of compound operators, and there's a unique parse tree corresponding to it. So the parse tree makes clear the structure of the expression. So what I'm saying is, given any expression like this, which is fully parenthesized, you know, there is a unique parse tree which corresponds to this. This is a very important idea. We'll be, you know, making this formal in, you know, after the midterm, you know, using something called context-free grammars. And you know, all programming languages, you know, have this structure. So your C programs have a parse tree, your Java programs have a parse tree, you know, all your arithmetic expressions which are computed by, you know, Mathematica have a parse tree, you know, and this idea of parse tree is very clear. It basically says there are some atomic things which we know how to calculate, and these are combined using, you know, some operators, and we know how to combine the results of the left argument and the right argument of the operator to obtain the result for the compound thing, right? Such definitions are called inductive definitions. So every pattern expression is constructed from atomic patterns by successive application of compounding operators like plus, you know, dot, star, etc. And parse tree makes clear the structure of the expression. And the language of the pattern expression can be computed in bottom-up fashion by applying the rules for each node. You know, at each node there is an operator, and for every operator we have given a rule. In fact, the definition takes the form of what is the rule for calculating the language of a pattern of the form plus of alpha beta in terms of the language of alpha and language of beta. Similarly, this rule says how to calculate the language of alpha dot beta by taking the language for alpha, language of beta, and applying this catenation operation to it, right? So we have one rule for every operator, and of course also for every atomic operator. And I hope you can intuitively see that these rules are sufficient to let us calculate the language, uniquely determine the language of every expression or every parse tree. Yeah? Any confusion here? Idea is simple. This example is simple, but this example is used by all compilers, you know, everything to actually compute the meaning of programs, you know, to compute the programs, or calculators to compute the expressions, you know, tools like Mathematica. Basically, we will have parse tree and we will know how to compute, you know, there will be rules telling you how atomic expressions are to be evaluated and how each operator is to be evaluated. And you successively apply those operations to obtain the result for the whole expression. Okay, so these are called inductive definitions, and the method is very general. It is used to define programming languages and their executions also. Okay, so I think we will be dealing with such inductive definitions very much in the second part of the course. But here the idea of language of an expression is clear. Now here, of course, we wrote expressions like this, right? And this was a fully parenthesized expression. It was like saying 1 plus 2 star 3. Okay, let me go to the next slide. You know what happened? Oh, I jumped to the end. Wonder how. Okay. Remember, in arithmetic, if we write something like 1 multiplied by 2 into 3, you know, I mean, naively we can say that this can be bracketed as this, or it can be bracketed as 1 plus 2 into 3, right? And then put bracket around this, and here put bracket around this. There are two, but we have conventions that star has higher precedence than plus, which means it binds tighter to its argument than plus, and hence this is the one that we take. These conventions we use in arithmetic, right? And this allows us to remove all these extra brackets, you know, which are cluttering up the expression. So we can reduce the bracket by defining what are called operator precedence. We'll do similar. So we will do similarly use operator precedence rules even for these patterns that we have got, you know. And what are the precedences? You know, star has the highest precedence. It binds to the thing nearest to it. Dot has the next precedence. Then, okay, I should have told you two more constructs that we have. We also have an intersection construct. So alpha intersection beta denotes the intersection of the languages of alpha and beta. So alpha intersection beta is L of alpha intersection beta. And this tilde of alpha denotes the complement, right? So we've got five operators, composition operators, plus, dot, star, intersection, and tilde, and we have got 5 atomic patterns, you know, these 5, and that defines the language of pattern expressions, right? And for that pattern expression, we know how to evaluate them. Here I'm trying to reduce the brackets, right? So just as we have operator precedence rules in arithmetic, we'll have this precedence of operators in case of pattern expressions. So I can, we also have associative rules, you know, alpha plus beta plus gamma is same as alpha plus into bracket beta plus gamma. You know, this is a property of the union. Whether you take And as a result, we can just write down as alpha plus beta plus gamma. So alpha union, beta union, gamma, you can bracket either in this way or that way, and it will give you the same result. So we don't really need to put these brackets. We don't need to make clear how the brackets are between alpha, beta and gamma when they are combined using only plus operator. Similarly, dot also is associative, right? So we will remove these brackets and we will use this precedence to remove some brackets. Okay. So I think when you read a pattern expression, you should apply this precedence rules. So for example, this thing that we saw before can actually be written as this with the precedence rule. Why is this the case? Firstly, you know, star binds the tightest. So this A star will give you A star bracket. Similarly, this BA star will actually reduce to this A star. And then this dot binds tighter than dot has higher precedence than plus. So this B will come here and there will be a bracket here. Similarly, this B between B and A star, there is a dot. So I'll get B dot A star and a bracket there. And then the plus has the least precedence. So I will get this and this is what I get. So I hope you are very clear. I mean, you have done this kind of things in arithmetic. So same thing is happening. This expression, which is fully parenthesized, can be written as this by removing some parentheses, you know, using these rules. So we will typically not write extra brackets, right? And you should be clear about how the brackets are to be added. Once the brackets are fully added, we get a unique parse tree, you know, of the kind that we saw here, right? Once the brackets are there, it makes clear the structure of the parse tree. Okay. And so with this operator precedence, a pattern like this will give you a unique parse tree, and then you can evaluate it bottom up to get its language. So that is the method. Clear?
Sir, one question here. Like, why is complementation after catenation? Like, is there a specific? Generally in mathematics, doesn't it come the other way around?
Pardon? What did you mean? We'll go to complementation. Yeah. What were you saying?
No. The order of operators.
Huh. Oh, well, it's a matter of convention, you know, and this is what is used in all books. So, you know, this is the definition, right? You cannot argue with the definition. I think it becomes more natural to have this complementation as higher precedence than plus or intersection. This is how we define it, right? It's a matter of convention.
Yes, generally I've seen that even higher than catenation, not necessarily catenation, but rather multiplication in those contexts.
I think here this is the order that at least I guess. I will check again in the books. I believe that dot has higher precedence than not. So for example, if you've got tilde of AB, right? What does this mean? This means A dot B and then you take tilde. It does not mean not of A dot B. So when you write tilde of AB, you mean something like this and not this. You could have chosen either this or this, but I have chosen this. OK. And sometimes in these things, the choice is a little bit arbitrary, but you have to choose one fixed thing so that in the rest of the class and in the exams and all, there is no confusion, right? So I think we are going to use the order which is given on this slides. OK.
Yes, sir.
Yeah. So let's stick with this. Now we'll have to choose some convention, right? So this is the order that I have chosen. Now I will use those orders in this example. OK. So firstly, what is the language of at?
Sir, your battery is low.
Oh, my battery is low. Yeah. So thanks. Yeah. Every time this happens, and I have no earth in my new house, so it gives me shock when I plug in battery. OK, fine. So what is the language of at? What is the rule for at? We have to go back to this slide which defines the rule. What is the language of at? Sigma star, right? So I have here language of at is same as sigma star, which is same as what is the language of hash?
Any letter from
Single letter, sigma. So the set sigma, right? And when you apply star operator to it, to hash, you will apply the same star operator, Kleene closure operation to this sigma. So what you will get is sigma star, right? So you can say language of hash star is same as language of at, which is sigma star, right? Clear? So actually we need not have this at in our pattern language. We could have replaced it by hash star. Wherever at occurred, you could have replaced it by hash star and reduced the language. You did not need at in your language. It is just an abbreviation if you like. So is this point clear to you? Yeah, I put all the examples in a single slide. So I hope this first example is clear to you. If there is any doubt, you ask. What is here is a pattern expression A star B star. What is its language? So I'll what will be its language? A raised to n greater than equal to 0, catenated with B raised to m greater than equal to 0, right? So this will give A raised to n, B raised to m, nm greater than equal to 0, but with no relation between them, right? So this is the language of AB star. What does this denote? An arbitrary string from sigma star followed by an A, followed by an arbitrary string, followed by letter A, followed by an arbitrary string, followed by letter A, and followed by an arbitrary string. This arbitrary string can even be epsilon. So what I'm saying is words with 3 occurrences of A in them. So this pattern denotes word with 3 occurrences of A in them. Suppose I wanted to yes.
It should be at least 3 occurrences of A, right? Because any word from at can also have
with at least. You are right. You are absolutely right. So, okay, I think I stand corrected. To be more precise, at least. So when I said 3 occurrences of I meant at least 3 occurrences of A. You are right. You are right. Suppose I wanted to define a pattern where I had an occurrence of subword AAA in it. How would I define this as? I would have an arbitrary 8 AAA and then an at, right? This will match with an arbitrary substring. This may in fact even contain AA inside it. We don't care, you know. So this AA we may match with the first occurrence of AA or with some middle occurrence of AA, and this is the remaining string. So this basically will match all strings of the form X followed by AA followed by Y, right? Where X and Y are arbitrary, right? So the language of this will be something like this, right? So you can see there is a lot of non-determinism if you like to think operationally in these patterns. What does this denote? What is this hash A? Okay, there is no A here. This is to be deleted. Huh? This blue part is not there. So what is hash? Oops. And here there is a, if you allow me, there's a tilde missing, right? So hash intersection tilde of A. What does that denote? And then it's star closure. So I'll write this on the next page and then we will say, you know, hash intersection tilde of A. What does this give us? Anybody can tell me? What will tilde of A give me? Any string which is not a single letter A. So it will include things like B, AB. It will also include AA, but it will not include this single letter A. Everything other than single letter A will be there, right? When we take its intersection with hash, what do we get? So meaning of hash is sigma. Sigma intersection anything other than letter A will give us sigma minus letter A. That is all letters of the alphabet, all single letters of the alphabet other than A, right? This is what I will get. Do you see this? And so if I now apply star to this sub expression, what will I get? I will get star of this, right? So I'll get sigma minus A star. That is any string which is made out of letters other than letter A, right? So it will include strings like, B, B, C, D, even epsilon. A should not occur anywhere in it, right? Because we have taken sigma minus A as denoted by this and taken its Kleene closure. So I hope this example is clear to you. Okay. Now here I want to define sentences. Sentences are just strings of alphabet symbols like dot, comma, etc. and blank. So sentence is also a word in formal language theory, right? It's a sequence of symbols, including symbol blank, right? And I want to talk about sentences having cat in it and nation in it, right? So I will define it as what? I will say arbitrary string followed by cat followed by arbitrary string. And then these arbitrary strings, any sequence of English characters, including blank, comma, etc., can occur, right? Here I define all those strings where nation occurs somewhere inside it, right? And then I take intersection of these two, right? So I'll get all those words in all those sequence of characters in which cat occurs somewhere as a subword and nation occurs as a subword. So this first blue sentence will match with this pattern, the nation of cats, because there is somewhere this nation and then there is this cat, right? Even the right hand side blue will match with it because there is a cat here and there is a nation here, right? So I can define things like that. And actually patterns like this are used a lot in, some of the natural language processing tasks. Now, both the textbooks, Cozen as well as Hofcroft, give lots and lots of examples of such pattern expressions. And I would urge you to read many more examples there so that your intuition about defining languages using such pattern expression becomes clear. Okay, so I will just do these many examples and continue. Okay, but you should read more examples from the book. Okay. Next, we define the notion of equivalence of two patterns. We say that a pattern expression alpha is equivalent to pattern expression beta if and only if the language of alpha is same as language of beta. And this can happen. In fact, here we saw two patterns, at and hash star. These two are equivalent, right? Because they denote the same language sigma star. So we define two patterns to be equivalent if their language is at all. This equivalence is also called language equivalence. So the notion of equivalence of patterns is clear to you. It's like saying that 2 plus 1 is equivalent to 3. We just write equal to because we don't know. If we treat this as expressions, then these are not same expressions. They are not identical. They are equivalent expressions, right? So similarly, we can talk about two patterns denoting the same language. Okay, the idea is clear. So for example, if you've got A plus B in bracket catenated with C, this is same as A catenated with C plus B catenated with C. Do you see this? So this kind of distributivity law holds between dot and plus. Just as you had distributivity between multiplication and addition in arithmetic, you have this kind of distributivity, okay, over patterns. How can we prove such an equivalence? Well, we have to evaluate the language for this, the left-hand side. We have to evaluate the language for right-hand side, and we have to show that these two languages are the same. Okay. But that is easy to see. You will get the language containing only A, only B. So we will get a language containing only A and B. And then when catenated with C, language containing C will give you AB, AC, BC, right? And right hand side will also give you. The left hand side will give you, AC, and then you will take union of that with BC. And so you will get ACBC. So both sides will evaluate to the same thing, and you can easily check that LHS language is equal to RHS language, right? By using the definition of the language of the expression. Okay. So we have this notion of equivalence of patterns, and because of this, using this notion of equivalence, we can show that a lot of operators are redundant. For example, hash can be written as, suppose my alphabet sigma consists of, it's a finite set of letters, right? It consists of letters A1, A2 up to AN, right? For example, if I had something called digit was my alphabet, this will consist of letters 0, 1 up to 9, right? And hash I can then write as A1 plus A2 plus A2. That is, I can write this digit equivalently as the following expression: 0 plus 1. Don't confuse this plus with arithmetic plus. This is our plus in the expression language. 9. This will exactly give us this set digit, right? So hash is redundant. At can be written as hash star. So the idea is that wherever hash occurs, we can substitute it by this. So the left hand side can be substituted by this, and hash can be removed from our expression. So we'll get a simpler expression, maybe larger in size, but which will not be using hash. Similarly, wherever at occurs, we can first substitute it by hash star, and then this hash we can substitute by A1 to AN, and hence we will get an expression without hash as well as at. Okay. So hash is redundant, at is redundant, intersection is redundant, because we can write using De Morgan law for intersection and union. We can write down intersection in terms of complement and union. Okay. So wherever intersection occurs, pattern of the form alpha intersection beta, we can write it as this. Okay. So what will happen is, as a result of all this, we will get a pattern. By applying these first 3 rules, we'll get a pattern which will not use hash, we will not use at, and which will not use intersection. It will use the remaining operators. Now what we are going to do is, I will let you into a secret. Tilde is also redundant, but let us assume that that we don't know. So for every pattern which uses tilde, we can come up with an alternate pattern which is without tilde, but let's not worry about that. What we will do is we'll define a subclass of pattern expressions called regular expressions. And in this regular expression, these operators are not allowed. So we have simpler class of expressions, right? They are just pattern expressions where we don't make use of these operators, right? Right? And this kind of patterns will be called regular expressions, or regex for short. And let's use letters alpha. This should be beta, alpha, beta to range over regefs. Then the what is called abstract syntax of regular expressions is defined here. A regular expression alpha is either constructed out of an atomic pattern letter A or B, or some letter of the alphabet, or the symbol phi, or the symbol epsilon, or it is constructed out of sub-regular expressions alpha and beta using the dot operator or a plus operator or a star operator. Okay, so these are the only operators allowed. Here we ignore bracketing, assuming that bracketing is clear by convention, and this is how every alpha can be constructed. So we will see in later part of the course, this is called the grammar for regular expression. Okay. So we will be, but is the idea of what is a regular expression clear to you? And we will see some examples. So here is a regular expression, because it uses, our alphabet is of course 0 and 1, right? And what it is doing is 1 1 plus 0 whole star 0. It is neither using at, nor using at, nor using hash, nor using complement, right? So this is a regular expression. Okay, so we'll mostly be dealing with regular expressions. Okay, and there's a good reason for dealing with regular expression. So the question before us is, what kind of languages are defined using regular expressions? And are these languages such that they can be accepted by DFA? Because if they are languages which can be accepted by DFA, in order to match words with those regular expression patterns, we can use this DFA to accept those words. And these DFS can be automated as digital circuits or as C programs. So we'll be able to do pattern matching using computer. That is why this question is important. And here is an example. Firstly, can somebody tell me what language does this denote? See, it's a catenation of two things. There is the first sub expression followed by second sub expression, which says either you have got 1 1 or a 0 repeated arbitrarily many times, right? Followed by either 0 0 or a 1 repeats arbitrarily. So you can't have 1 0 1 0 in the first part, and in the second part also you can have 1 0 1 0. You will have some repetition of only zeros or 1 1s, etc. And you can see that this regular expression is actually denotes the same language as the language accepted by this automaton. First, you are in this state where you will accept either a subword 1 1 by taking this arrow and then this arrow and then this arrow, or you will take a 0 and then this thing can repeat any number of times, right? So the first sub expression is denoted by this blue arrow marked sub automaton. And then you want to do the remaining expression. So you do an epsilon transition and then you detect the subword which matches the second half of the regular expression, where you can either have 1 or a pattern 0 0, and this is repeated any number of times. So I hope you are able to see how the top regular expression denotes the same language as the language accepted by the DFA, NFA given, epsilon NFA given below. Just try to visualize what does 1 1 plus 0 star mean. You know, the whole string can be broken into chunks where each chunk is either 1 1 or it is a 0. And it's a sequence of such things. Maybe there's another 0 and then there's another 1 1 and maybe then there is another 1 1, something like this, right? So the whole string can be broken into chunks where each chunk is either a 1 1 or a 0. That is accepted by either you accept that chunk using this transition or using this subpath which accepts 0 0. And you go around this any number of times to accept any of these. That denotes the language of the first half. The language of the second half is denoted by this sub-automaton, and you do the first part, then do an epsilon move, and then you go to the second part. So I think it is not very difficult to intuitively see that this regular expression has the same language as the language of this automaton, right? And this is an epsilon NFA, but you can determinize it. So you can get a DFA equivalent to it and then implement it in your C or digital circuit. So this regular expression could be done by a DFA. But what about in general? So what do you think? Can matching for the language of any regular expression be done using a DFA or not? What is your guess? I unfortunately don't have know how to do the poll online, or I would have asked you to answer yes or no. But this is the question. Ishan okay, some people are saying yes. Is there any no? Don't worry. I mean, you don't have to know the answer. This is just your intuition at this point. You don't have to be right in your intuition. This is not a question which is obvious just by looking at things, right? We are talking about any arbitrary regular expression, and we are asking whether there is a DFA which will accept this language or not, right? So these are the kind of questions we ask in this course. Okay, another yes. Any no's? Okay, 2 people have said yes. So I think that biases the rest of the people's intuition. Anyway, here is the theorem. Don't worry. For every regular expression alpha, we can actually construct a normalized epsilon NFA called A of alpha, such that the language of alpha is same as the language accepted by A of alpha. Remember, language of alpha was defined using those rules. Right? We had one method of calculating language of an expression. Language of an NFA was defined by, checking paths which take you from start state to accepting state in an epsilon NFA, right? But we are saying that these two notions of languages match. And hence we can convert every regular expression into a language equivalent epsilon NFA, and then we can determinize it, and then we can implement it in a program or a circuit. Okay, so this theorem is true, and this theorem was proved by a very famous mathematician called Kleene. Okay, so he's famous for this. This is called Kleene. This is in fact half of Kleene's theorem. Okay, we'll see the other half also, maybe in the next class. So, but first let's prove this theorem. It's not very difficult to see. And this theorem is also proved by structural induction, right? So, just as we defined the language of an automaton using its parse tree in a bottom-up fashion, see how did we define the language of an automaton? This way. We first calculated the language of the leaf expression, which was this language containing a single word A. Then we constructed the language for the next higher node, which was A star, and then we calculated the language for this leaf expression B. And then for this dot, for this subtree, we calculated the language by composing the languages for the left subtree and the right subtree using the catenation operation, right? So we went bottom up constructing the language. We will do something similar. We will construct epsilon NFA for each of the leaf nodes, which represents its language. And for every node, given the automata for the left subtree and the right subtree, we will construct the automaton for the tree, right? So if we know the automaton corresponding to these two blue circles, we will construct an automaton corresponding to this node, so that this sub expression will have same language as the language of the automata we constructed. In this, we will assume that the automaton we constructed for this blue part is same as the language of its sub expression. So, same inductive way of working bottom up, which we used to define languages, we will now use that bottom up approach. This is called the inductive approach. Start from simple things, combine them, because the operators combine simple expressions to form bigger expressions, combine simpler automata to get bigger automata for the language of a complex expression, right? This inductive method is what we will use to construct the automaton for the whole expression. So is this bottom-up inductive way of working clear to you? To be used many times. In fact, it's one of the main techniques used in this course and in computer science. Okay, first we were calculating language. Now we are going to construct automaton for that language in the same inductive way. So what are the kind of rules we have to give? We have to first tell you what are the automata for atomic patterns, right? Basic patterns should correspond to some normalized epsilon NFA. So I have three patterns, the single letter A, and that is actually accepted by this normalized epsilon NFA. It has two states, S1, S and T, right? And S is the start state, T is the final state, and there is a single transition on an A from S to T. If any letter occurs after that, you reject. If any letter other than A occurs, you reject. Right? So this automaton, you can see exactly recognizes a string consisting of a single letter A, which is the language of this atomic pattern red A, right? So is it clear that this atomic pattern red A is gives the language which is accepted by this automaton, the curly bracketed automaton? Anybody has any confusion there? So for this one particular pattern consisting of red A, we have constructed an epsilon NFA. Similarly, for the pattern red epsilon, it should accept only the empty word, and it should not accept any other word, right? So we'll construct this automaton, this second curly bracketed automaton. And you can see that, of course, it will accept epsilon because the start state is same as empty. If any letter occurs, it has to move out of that. The run will die and we won't accept it. So the language of this second curly bracketed automaton is just the language containing the empty word. So again, for this red epsilon pattern, red epsilon regular expression, we have constructed an epsilon NFA, right? In fact, it's a DFA. Both of these are DFA and they are in normalized form. For empty set, for the regular expression phi, which denotes empty set of words, no word will match with it. We'll have this automaton with a single state, which is not an accepting state. And if any letter comes after, so it will reject epsilon also, and any letter comes after it, the run will die and we will not accept. So we will not accept any word. So I think for the 3 atomic patterns, of the regular expression, we have constructed, DFAs, which will recognize them. And these are normalized. Any confusion here? So we convert A into this automaton, A into this automaton, epsilon into this automaton, and phi into this automaton, right? So wherever A occurs, we'll have this sub-automaton. Wherever epsilon occurs in the pattern, we'll have this sub-automaton for it. And wherever phi occurs, we'll have this sub-automaton for it. Idea is clear. For the simple kinds of regular expressions, we are able to convert them into normalized epsilon automata, right? We don't have to use epsilon, we don't have to use non-determinism, but we can if we need. Here we don't use them. So I hope this is clear to you. Any confusion and you should ask me. Okay, if this is clear, very simple. Suppose we have a sub expression of the form alpha plus beta, right? So we have, and we want to convert this to its equivalent automaton, which recognizes the same language. We inductively assume that we have already constructed normalized epsilon NFA, A of alpha, A of beta. And A of alpha accepts same language as the language of alpha. And A of beta, which is an automaton, accepts same language as beta. Now, plus denotes union. So we will take an automaton which will recognize union of these 2 languages. And this union construction we had already done in the last class and last class. This is the automaton for A of alpha. This is the automaton for A of beta. And we assume that they are in normalized form, because we inductively assume we have normalized automata for A of alpha and A of beta. We construct this normalized automaton for alpha plus beta. And it's obvious. We've showed that this recognizes the union of those 2 languages. So it will recognize the language of alpha plus beta. Nothing to it, right? So if we know how to calculate automaton for alpha and automaton for beta, we know how to calculate the automaton for alpha plus beta. Agreed? This is the induction step. That is from component automata, you compose and produce a beta automaton. Similarly, you can do for catenation also. If you know how to construct automata for alpha and beta, then you can get automaton for alpha dot beta, which is catenation of alpha dot beta, by this language catenation automaton, which does language catenation construction. We showed that regular languages are closed under catenation by doing this construction. So you first have the automaton for A of alpha, then do an epsilon transition after accepting using that, and then go to A of beta. And this will give you exactly language of A of alpha and language of A of beta as before. And similarly for alpha star, we have this construction. Right? So this construction we had already seen. If you know how to construct automaton for alpha, you can construct automaton for alpha star, because this is the automaton which takes the Kleene closure of a language, regular language, right? Given an automaton R for a language, we can get an automaton for its Kleene closure using this construction, which we had seen in last class, right? So given component automata of expressions, we can construct automaton for the composite. And now we can work in the bottom-up fashion as before. We start by constructing automaton for this A. From that, construct automaton for A star, this left circled part. You construct an automaton for B. Then you do the catenation operation on these two blue circled automata to get the automaton for this green circled part, right? So using this blue automata for blue circle part, you construct the automaton for green circle part using the automaton construction for catenation. Similarly, you do on this side, finally combine them using union, and by working in this bottom up fashion, you can construct the automaton for the whole expression. This is also inductive construction. These bottom ups, constructions are all called inductive constructions, and that is the main technique that we are using. Okay, last thing I want to do is I want to calculate the size of the automaton constructed. How large can it grow? For that, the size of the automaton constructed will depend on the size of the regular expression. So suppose we have got a regular expression alpha. What is the size of that regular expression? What we do is in alpha, we count the number of atomic expressions and number of composition operators used. We ignore the bracket, and that gives us the size. So suppose we have an expression a plus b star bracketed star followed by AAA. Remember, there is an implicit dot here, right? We don't write it, but there is a dot. So what do we have? We have got, how many operators, how many symbols are there in this? We do disregard bracket, one for an A, one for a B, one for a plus, one for a star. So we got 4, then we got 3 A's, so 7, and then 3 dots, right? 3 dots or 4 dots? 1, 2, 3 dots. So this should be 10. Okay, that was a mistake. So the size of this regular expression is 10 because it's using 10 symbols in defining it, right? This is how we define size of a regular expression. How large is the regular expression? And when we convert this to an automaton, we get the size of the converted automaton is of the order of size of alpha. That is, it is some constant times this. So, when we say that size of some expression alpha is order of size of beta, what do we mean by this? Have you done a course on algorithms where this big O notation is defined? It means alpha is of the form, some constant C1 times size of beta plus C2. And this constant C1 and C2 remain same for different alphas and beta. So you give me any beta, the corresponding alpha that I construct will be some sort of grow linearly in the size of beta. So the alpha will grow linearly in size of beta modulo some fixed constant, so it will be constants times size of beta roughly for large betas, right? This is the notion of big O notation in computer science. And what we claim here is that the size of the constructed automaton is roughly, some constant times the size of alpha. In fact, this constant should be specified by the method. So, this constant in our case will be something like 4 or something, 4 times the size of alpha, right? And maybe there will be some fixed constant, which is 0 in our case, right? So it will be 4 times the size of alpha in our case. Why is that the case? For every atomic operator, if you have got a single letter A, its automaton will have size 2. So it will be less than 4 times the size of A, right? Size of an automaton is counted as number of states. And so the automaton for red A has 2 states. So its size is less than 4 times the size of red A. Similarly, epsilon has got a single state, so its size grows proportional to epsilon. So if phi gives you an automaton with a single state. When you take union, you will get something which is linear in the size of alpha, something linear in the size of beta. So you will get size of alpha plus size of beta plus 2. That will be the size of my automaton for alpha plus beta. That is, if I know an automaton which is of the size of alpha, I know the automaton for size of beta, then I will add 2 additional states to it. So it will be, at most this. So you can see that basically in all these constructions, I am only adding constantly many extra states. And in fact, I am not adding more than 4 states. In fact, I am adding only 2 states extra. So I should have made this 2 times alpha plus 0. Okay, so what I'm claiming is that I will get an automaton for alpha, which is at most 2 times the size of alpha. That is size of A is equal to 2 times the size of alpha. That is my claim, right? And you can see that at every step I am maintaining this. Whenever I have an extra operator, I add extra only 2 nodes, right? So I have something which is linear in the size of alpha. Okay, so in some sense, you know, the size of the constructed automaton grows linearly in the size of the regular expression, and we don't get a very large automaton, epsilon NFA. Of course, when we convert it to DFA, we will get an exponential blow up, but at least the NFA is not very large. So we can easily convert, you know, a large regular expression into an automaton, which is not too large. Okay, at most double the number of states or something like that. Okay, that's what I wanted to do today. So what have we done? We have defined regular expressions. We have seen some examples of specifying patterns using regular expressions like this. And we have seen that every regular expression can be converted to its equivalent epsilon NFA, which is linear in the size of the regular expression, not too large, maybe 2 times, 3 times larger than the size, okay, of the expression. This is what we have done. And hence, regular expressions only define regular languages, because for every regular expression, there is an epsilon NFA. And so there is a finite automaton recognizing it. So the only kind of languages you will get using regular expressions will be, what is no, Ishan? No. Certainly not true. So I think this is an interesting question. And we will, Om has asked a question in chat. We'll specifically be dealing with this later, but it's a very good question. Yes. So what is the equivalent expression which does not use plus? Om, try to come up with one. Okay. So these are questions about equivalences of regular expressions. Interesting question. Okay, so I think we will continue with this topic in the next class. And you know, basically what we do in the next class, up to that will be the portion for the first mid-sem. Okay, up to regular expressions, nothing more. So everything that we have done up to this will be in the mid-sem. Now I'll release a homework, you know, by tomorrow morning, and you can try to solve the problems there. It will cover problems up to next lecture. So, you know, there will be a couple of problems in the homework which you will not be able to solve using lectures up to today, but most of the problems you should be able to solve. And let me tell you that midterm will be based on the homework problems. So it is in your interest to solve the homework. Okay. Okay, thank you.
So can you demonstrate another example of that size calculation?
Size calculation.
Yes.
Yeah, let us do. So size calculation, right? Yeah, let's add a page here. Suppose we have the regular expression A star B, right? What is it constructed out of? You know, what is its parse tree? The way in which it is constructed, there's a dot operator. Its right hand argument is B, its left hand argument is star, and then there is a A here, right? Now when we convert this to automaton, first we will convert it to automaton for A, which will look something like this, right? Agreed? This is the automaton for a single A. Now we have to take star of this. How did we take star of it? We added one more state here, one more state here. We put an epsilon transition here, right? An epsilon transition here. We had an epsilon transition going here and a back epsilon here, right? So the original, the automaton for A had 2 states in it. Size of the automaton for A was, so automaton for A, the size of this was equal to 2 was equal to 2 times the size of A, because A gives you size of 1, right? So the size of automaton for this leaf node is at most double the size of the expression. Next, for star automaton, what is the size? It is 4 nodes, right? And what is the size of A star? So automaton for A star, right, has got size 4, which is equal to 2 times the size of A star. Why is the size of A star 2? There is a letter A and there is an operator star. So if A star gives you size 2 and 2 times 2 is, so you can see that the size of A star remains within 2 times the size of expression A star. Size of automaton for A star remains 2 times the size of expression A star, right? Did you see that? So for this, we have shown that the size of the automaton of this green circled expression is 2 times the size of the expression. What is the size of the green circled expression? 2, right?
Yes, sir.
So for any sub expression, the size of the automaton will at most be 2 times the size of this. Now for B again, it will be 2, right?
Yes, I mean independently 2.
Yeah, it will be 2, right? Here it was 4. And when I take dot, what do? I take these 2 automata and put them together with just an epsilon. I don't even add any extra state. So I'll get 4 plus 2, 6, right? 6 is the size of the automaton here, right? But what is the size of this expression A star B? It is 3, right? A contributes 1, B contributes 1, and star contributes 1. And 2 times 3 is 6. So I'm always staying within 2 times the size of the expression. So my automaton is no larger than
4, right?
A
It'll be
star
4.
dot B.
A star dot B. Yeah.
Okay.
So actually the
4.
size is 4. So I'm allowed to use up to 8 states in this. But BIGO says that upper bound is 8. And I'm actually using only 6. So this BIGO notation does not give you the exact number of states. It says upper bound on the number of states in the automaton is at most this. Okay.
Sir, can that be a big theta notation?
Yeah, but
That-
we are not using theta because sometimes the automata can be smaller, as you saw in this example. So it's very difficult to predict what will be the smallest size. Okay.
Yes,
So
sir.
we are using
is that
BIGO, only giving an upper bound.
For or against that for a big theta notation?
I will not deal with theta notation in this course, but I think at some point as computer science minors, you're going to do a course on design and analysis of algorithms, right?
Yes, sir.
Okay, we'll see if we get a chance. I will introduce you to theta notation somewhere in future. But here we are talking about BIGO. So BIGO means upper bound. Okay.
Yes, sir. This section is clear. No issue.
Yeah. Theta we are not doing yet. Okay.
Sir,
Yes.
in the theorem that you discussed about regular expressions,
This.
yeah, is the converse also true?
Very good question. I'm so glad in this class people are asking questions. It turns out that the converse is true and the proof is little hard. That is the topic of the next class. So I told you this was half of Kleene theorem. The other half is the converse. And the Kleene theorem is that the converse is also true. For every automaton, every NFA, we can construct a language equivalent regular expression also. Okay, so good question, but we'll see it in next class. Who was asking the question? Can you say your name, please?
Ishan.
Okay, fine. Yeah, so that sets up us for the next class. Very good.
So also with regards to redundancy of complement, like how does that expression transform into? Is there like a procedural way it just transforms into,
Okay.
or like is that
Who's
case
asking this question?
Arvind?
Arvind, again, another excellent question. Let us take it up in the next class. So I'll remember both these questions, and in the next class, we will deal with that also. What do we do with complement? And what will be the equivalent expression like, right? It's
Yes,
not
sir.
very straightforward, but the next lecture will give you the answer. Okay?
Okay, sir.
So both very good questions. In fact, it is after asking both the questions that you have asked, some of this theory was developed, and then the results were obtained by some very famous logicians. So the half of the work in research is to ask the right questions. And then you go for the answer. Sometimes the answers are obvious, sometimes they are not obvious, and you have to do a lot of work. And when that happens, you write a paper, and then sometimes that paper becomes famous. So this is the way to research. Excellent. Okay. So 2 good questions which we will deal with in the next class. I think we have overshot our time, so I should stop the recording at this point. Are there any other questions, please? Okay, nothing else is coming.